So we were at the simultaneous eigenvectors theorem, which essentially said that two normal operators have simultaneous eigenvectors if and only if they commute. So, well, the if part of the proof was rather trivial. So simultaneous, I assume they have simultaneous eigenvectors. I can carry out a spectral decomposition of each of the vectors and I can show that they commute. So this is rather trivial. What about the other direction? The proof that if A and B commute, this implies A and B has a common set of eigenvectors. So what I do is I start with the spectral decomposition of A, where P lambda is projector in the subspace S lambda. The subspace which would project back, these subspaces are labeled by the degenerate eigenvalues lambda. So that's my spectral decomposition. Now, what's the deal? So now consider a vector. Consider a vector in one of these subspaces, and if I compute this guy, which is nothing but, since A and B commute, this guy is equals to this guy. Since A was an eigenvector, this was an eigen subspace with the eigenvalue lambda. So I'm just plugging in the definition. So what does it say? This guy. This relationship says is that this element is an eigenvector of A with eigenvalue lambda. So therefore this guy also belongs to this subspace. Now what does it mean? It means a vector which is an element of the eigen subspace of A gets mapped back to the subspace by B. So I'll just write down B as a sum of such decompositions where each of these B lambda acts in S lambda, this subspace. That's essentially what's happening, because I can carry out this process for any E belonging to different subspaces, and in those subspaces the action of B is to map back the vector into the same subspace. So I am just going to write down B as a combination of such a decomposition, each characterized by B's of lambda, where B's of lambda is acting in the eigensubspace of A. So now it's easy to see, because diagonalizing each of these B lambda gives us eigenvectors that belong to S lambda. Because see, B lambda was acting in S lambda only, that belong to S lambda, and therefore are eigenvectors of, and therefore are eigenvectors of A as well. So that in a way completes the proof. Of course, notice that if B eigenvectors from different S lambda, different eigenspaces of A are degenerate, then we can superpose them to make B eigenvectors that do not lie in S lambda. Then we can superpose them to make B eigenvectors that do not lie in S lambda. So that's a sort of a side point, that not every eigenvector set on B would be shared by A, but this is sort of a constructive proof that let's say we did not have this sort of a condition, then they do share indeed. There exists a way to assign eigenvectors to both A and B so that they share the same set. Okay, so that brings us to just quickly summarize the axioms of quantum mechanics, which we've already done since this was in the notes itself. So if this is a repetition and I have done it, I don't remember frankly, so apologies, you can just skip this part. Axioms of quantum mechanics. So this was our state vector, and this is equivalent to this guy, which we call as a ray. So these state vectors describing a quantum mechanical system are equivalent up to a scalar. We usually deal in normalized vectors, so I'm going to represent it by this guy. And any particular phase I can tack along represents the same state. The observables are given by Hermitian operators. So we've already seen the measurements are the eigenvalues of the observable, so better be an operator with real eigenvalues. Observables are Hermitian operators. Results of measurement is one of the eigenvalues of a result of measurement of an observable A is one of the eigenvalues of A, and if I can express the state in the basis of the eigenvectors of A, so these were the eigenvectors of the observable, eigenvectors of observable A, then the probability of getting the outcome EJ is just this guy, the absolute value squared of the coefficient. This is the Bond's rule. What about the post-measurement state? Post-measurement state. Well, that is just a measurement with the result EJ leaves the system in EJ. So that's when I say that an outcome, the state has collapsed into. So when I'm going to measure an observable, this is the number I'm going to record on the screen, which is going to be the eigenvalue of that observable, and the state of the system would collapse in the eigenvector corresponding to that particular eigenvalue. So this is going to be the state of the system upon getting the eigenvalue lambda j of A. This guy, I'm just normalizing it. And what about the dynamics? Well, the time evolution is governed by something called as a Schrodinger's equation, where H is the system Hamiltonian. So, in other words, the state vector at time t is equivalent to, I think I'm missing a minus sign somewhere, so you guys just fix it. It's equivalent to the initial state vector, and this is a unitary evolution. So the future state of the system at time t is related to the initial state of the system by a unitary evolution. This is going to be a unitary operator since H is a Hermitian operator. So this is just a solution to this equation, the Schrodinger's equation. So yeah, there we go. This essentially is, yeah, I think there's a minus sign over here. So this governs the quantum dynamics. Yeah, so till then, see you next time.